rational function f of x. We're going to try to get an idea of what it looks like, both with and without graphing technology. Of course, that would require us knowing its main features, which would be its intercepts and asymptotes and the like. So to figure all that stuff out, let's factor the numerator in this rational function. So f of x, since there's a quadratic, we can break that down into x minus 2 times x plus 1. Of course, what adds to give me minus 1 and multiplies to give me minus 2. But hopefully that's old news at this point. And then we have our original denominator, x minus 2. And I'm sure you've noticed that we have a factor, x minus 2, in the numerator that matches the factor in the denominator. So we can actually divide those two factors, and we'll get the number 1, of course. That'll divide in evenly. So it looks like our function, rational function, just becomes a little old f of x equals x plus 1, a straight line. Now, you should be a little bit confused by that. How does a rational expression just turn into a straight line? Where did my asymptotes go? And all the normal features you would expect to see in a rational function. Well, the issue is we still have to keep our domain restriction. F of x is x plus 1, but x still can't be equal to 2. So it's not quite a straight line. It's awful close. So x can't be equal to 2. And just to make sure we understand why, if I go back to my original function, if I put 2 into my original function, my numerator, I get 2 squared minus 2 minus another 2. And in the denominator, I get 2 minus 2. You can see that something unusual happens. You get division by 0, but what's worse, you have a 0 in the top as well. And that's called indeterminate form. And if you get division by 0, that means, of course, you have a domain restriction that you're dealing with. And if you get 0 over 0, that should tell you that you have a little bit of algebraic tinkering to do to simplify this expression into a more basic function, but you still have to keep the domain restriction. And what's a little bit confusing, if we look at our f of x equals x plus 1, it looks like we can put in our value, x value of 2, down here in the simplified version, right? It looks a lot like we can just say, hey, 2 plus 1 gives me 3. So isn't the y value of this function equal 3? And the answer is no. Even if we're dealing with the simplified one, we have to keep the domain restriction alive, so to speak. So f of 2 down here is still undefined, since it was undefined in the original. Of course, that's mainly because of the denominator there. So you should be asking yourself, well, what does this thing look like? Well, let's have a look at the graph with our graphing technology. Okay, so let's go ahead and graph this rational function. Of course, we'll open up a new document here and graph f1 of x. I think the easiest way would be to put in our fraction template there, so we don't have to use as many brackets. And then we'll, of course, type in the numerator, x squared minus x minus 2, and then the bottom, x minus 2. And then if we graph that, lo and behold, it looks like it is a straight line. And what I want to convince you of is that if we hit trace and try to evaluate this function at x equals 2, and notice we have no problems if we put in 1.5 and 1.8 and whatever values we get. And unfortunately, our calculator's not zooming right in on that area of x equals 2, so we have to physically type in x equals 2. And then we get this. It says f of 2 is undefined. So exactly what I told you happens. You still have your domain restriction of your original function. And now that looks like there's a vertical asymptote there with that dotted line, but of course around a vertical asymptote you would expect a function to kind of go berserk and go off your graph paper, approaching positive or negative infinity on either side of that vertical asymptote. So this is not a vertical asymptote. This is something called a point of discontinuity. Okay, so back to our written work here. Of course, we still see our simplified function f of x, and I just went ahead and graphed that straight line. Now this is pretty much what the line looked like on in our graphing calculators, graphing window. But of course, we have to exaggerate what's happening at x equals 2 to get this point of discontinuity in. And just a quick recap, of course, graphing y equals x plus 1, you can just sub in some x values. If x is 0, of course, y is 1. If x is negative 1, you get y is 0, etc. So what do I mean by trying to exaggerate what's happening at x equals 2? Well, if I find x equals 2, I can see that that is the location on my graph that my function is undefined. So we actually just notch it out, which your graphing calculator doesn't do, and we try to put an open circle there. And that open circle is called a point of discontinuity. We usually just abbreviate it as a POD. And where does that point of discontinuity happen? Of course, it was at the original domain restriction on our f of x function, which of course you can look in the denominator and figure out where that happens. And notice, what is the y value of the point of discontinuity? And that's, of course, you can find the y value by inputting this into your simplified function, right? So please be careful that you don't think that the function is actually defined at 3. It's just simply the location of the point of discontinuity. So if I come down here, I can figure out my point of discontinuity's y value is going to be at x equals 2, or 2 plus 1 in that simplified function, or of course 3. And you can see that that makes a lot of sense based on the graph of this function. And also, keep in mind, this is not a vertical asymptote, even though there's a break in our function. If I get close to this point of discontinuity from the left or from the right, I don't see my graph or my function zooming off my graph paper and approaching positive or negative infinity. I just see my function getting closer and closer to the y value of 3 as my x values get closer and closer to the x value of 2. Okay, let's have a look at the limit of this function as x approaches 2, and that's the location of our point of discontinuity. You can see I have the x value of 2 highlighted with a red dotted line, and we can see the output of that function. It's not exactly 3, but it's almost like it wants to be equal to 3. So if we evaluate the limit as x approaches 2, we have to consider approaching 2 from both sides. So if x approaches 2 from the left-hand side, we can see our function values seem to be getting closer and closer and closer to the y value of 3. And similarly, from the right-hand side, if x approaches 2 from the right-hand side, we can see our function is also trying to get close to 3. Now it's getting closer to 3 in two different ways. From the left, we can see our y values are approaching 3 from underneath. And from when x approaches 2 from the right, we can see y is trying to approach the number 3 from above. But regardless, we can see those arrows coming together. So we can say the limit of this function as x approaches 2 is equal to the number 3. So when we have a point of discontinuity, a simple hole in our function, the limit actually exists, and it's in this case the real number 3. So make sure you understand that if you're going to evaluate a limit at a point of discontinuity, you should at least consider, if not write down, the two what we call one-sided limits, like we just illustrated on the graph paper here. If I try to evaluate the limit of this function as x approaches 2 from the left, then we can see the y values are getting closer and closer to 3 from below. And again, if x approaches 2 from the right-hand side, the limit of this function is also 3 from, I guess, getting closer and closer from above. So considering both of these so-called one-sided limits, and the fact that they're both equal to each other, and they both are equal to the real number 3, we can say the two-sided limit, or the limit as x approaches 2 of this function, is equal to 3. So those are some finer details there, but just basically understand one thing about limits. If you are saying this limit, in this case, as x approaches 2 exists and it's equal to 3, you are saying that as x gets closer to 2 from either side, the y values will inevitably get closer and closer to 3. And I think it'd be a good idea to look at a table of values here just to be really clear why we can say the limit of this function as x approaches 2 exists. So if x equals 1, our function is 2. If x is 1.5, or 1.9, or 1.99, or yes, 1.39s, we can see that if x gets closer to 2 from the left, the function gets closer to 3 from underneath. And if x equals 2, our function is undefined. Now from the right-hand side, if x approaches 2 from the right, like 2.5, or 2.1, or 2.01, and yes, 2.001, we can see that our function value is getting closer and closer and closer to 3 again. So the behavior at x equals 2, even though the function is undefined, we can say the limit as x approaches 2 of this function equals 3, because we can see if x gets close to 2 from the left, the function gets closer to 3, and similarly, if x gets closer to 2 from the right, the function still gets close to 3.